Hi everybody, this is Vukcevic from University of Zagreb, and I'm gonna make a second, this is basically a second basic programming training in OpenFOAM, where I will show you how to create your own basic boundary condition. Now the difference between the solvers and boundary conditions, for example, is solvers you compile into a binary file, and boundary conditions you can compile into shared object libraries, which enable you to dynamically link the libraries into existing solvers without recompiling. So the idea is fairly simple. We're going to use the solver passive scalar icofoam to run the cavity test case again, but what we would like to do is sort of create modifiable fixed value, actually varying fixed value boundary condition, where we will specify a maximum value, minimum value, and sort of a threshold value, and when the average of the whole internal field exceeds the threshold value, we will switch from the maximum value to the minimum value. So we're going to do it only for scalars, because this is a basic training. I don't want to go into details regarding templates. So let's start. The first thing we would like to do is find a similar boundary condition which we would like to start from. I went into a finite volume library, and in finite volume, just a second, no, in fields fv patch fields, this is basically boundary conditions. In derived, you have a list of boundary conditions. What I would advise you to do is just take a look through them and see if you need something. If you have something, or if you already have something that you need here, then perfect. If you don't, then find the sort of a closest match to start your code from. In this tutorial, I'm going to start from the total temperature boundary condition, which is specific for temperature field, which is a scalar. So this is why I picked this one. So first, I'm going to copy the total temperature boundary condition, total temperature here, and I'm going to rename it to, actually, I'm going to create, just reorganize a bit. I'm going to create a directory for solvers and move the old solver there, and create the directory for libraries. Actually, I'm going to call it src, and I'm going to move the total temperature into here. And total temperature, I'm also going to create actually another directory called my boundary conditions, and I'm going to move total temperature into here and rename total temperature into average control, because we're going to control our fixed value with the average field value. So the first thing is very simple. We need to, let's get rid of these dependencies. You can use remove dependencies, or remove all dependencies, rmdep all, which removes this dependency file, and now we are left with two files. And as before, we're going to start by renaming them. So total temperature will be average controlled, and we have renamed the h file, and now we need to rename the c file. Oh, wrong key. Now let's check the names: average control fv patch scalar field.c and average control fv patch scalar field.h. So basically, each boundary condition is its own class. You have the header file and the .c or implementation file. Now what we need to do is we need to tell the compiler what to compile, and for that we're going to copy the make directory from the finite volume library, the whole one. So if I just copy it, make, okay, I have a make file now, and then I will search for total temperature, and I will remove everything from this line upwards, and remove everything from this line, almost everything, down to down. Okay, I'm missing here Okay, so this is just one shortcut. We're not going to use that, we don't need it, and we're gonna replace all occurrences of total temperature with what's it called, average controlled. So now we have average controlled and average controlled fv patch scalar field.c. And now similar as with the solvers, we have here just a second, we have here compilation instructions. So instead of executable or exe, we have lib, because this is going to be a library, where to put the library and what's it going to be called. So as you can see, you have your environmental variable foam libbin, which is in your installation of OpenFOAM, but you also have foam user libbin, and for your development you should use this one. And now let's take a look where that one is, and it's in my directory here. And then if I do ls, I have some of my libraries I've been developing, and of course the name of the library will be now libmy boundary conditions. This is it. Now let me just check. Oh yeah, this make file should not be here, but in the parent directory. And now in make options, we have includes and additional libraries that we're going to use. And here we need to remember that we need to also include the, actually I'm going to copy this one, it's going to be easier. We need to copy the finite volume library, because this class will be derived from the abstract base class finite volume patch field that we are gonna redefine. So we need to have access to the finite volume header files in the finite volume library and the library itself. So it's called finite volume. Actually, let me check that just to be sure. If I go foam fv make files, it's lib finite volume, so it's finite volume. So now that we have created our make directory, let's go and take a look into average controlled fv patch scalar field.h. So again, you have a header file with a license, information about class, description, and the list of source files. Here we have only one. So the first thing we're going to do here is we're going to search and replace for total temperature and replace it with average controlled. Now let's take a look. This is just the class name, source files. Okay, header inclusion, protection, just some comments, type name, constructors. We're just gonna do a global replace. I wanted to do it step by step just to show you briefly. And of course this is, we're going to do the same in the .c file. Constructors, member functions, etc. So now let's start from the beginning. What we need to do is first of all change the description. We're gonna say something like boundary condition switches between maximum and minimum specified values for a scalar if a weighted average is larger than the threshold value set up by the user. So now all of these classes are basically defined in the foam namespace, and here we define the class average controlled FV per scalar field. Declare the class average controlled FV per scalar field, which is derived publicly from fixed value FV per scalar field. Why fixed value? Because this is just a fixed value boundary condition which changes itself in some way. These are the private data members of the class. You can actually recognize them by trailing underscores. This is just an OpenFOAM style which you should use consistently. All data members, first of all, should be private and should contain trailing underscores. So what we need here is basically, as we said, we want to have maximum, we want the user to specify maximum and minimum values and the threshold value. And if the average value in the field exceeds the threshold value, we'll switch from the maximum to the minimum value. So now, excuse me, first we're going to set up maximum value. We're going to call it's a scalar because this is a scalar field. I didn't want to do it generic in this at this level because this is just a basic tutorial. I didn't want to spend a lot of time into discussing templates. So we're going to have scalar psi max. This is just a name. I'm going to call it generally psi. Actually, let's remove all of these old ones before associated with total temperature boundary condition. We're not going to need them. And now let's copy this twice. So we have maximum value, we have minimum value, we have threshold value. And now we have some public functions. We have runtime type information, just the name of the class basically. Constructors, we have a lot of different constructors, from patch and internal field, from internal field and dictionary. This is the one we're going to actually use at the moment. Mapping, copying, cloning, etc. By changing our names from total temperature to average controlled in all of these, we don't really have to do anything else at this moment. So also it's a good idea to provide some basic access member functions because all of our data is private. So let's return the maximum value, maximum specified value. And this function is going to return a scalar by value. Maximum value, we're going to call it maximum value, and return psi max. And this function returns a scalar by value, is called maximum value, doesn't take any parameters. It is constant because it doesn't change data members, and it's implicitly in line because its definition is inside the header file. Let's remove these, and now let's just copy these two once and twice. Now return the minimum specified value, C min, and return the threshold value. All of these are scalars and constant functions. So now we have some mapping functions for automatic mapping and reverse mapping. We don't need to take care of these. And we have evaluation functions. This is where the magic will happen. In total temperature boundary condition, SN grad and gradient internal and boundary conditions were redefined. We don't need that at the moment. We're just gonna take a look at the update coefficients. And of course we have a write function which will take care of the writing when you specify the write in when you specify the write interval and controlDict, the patch fields, boundary fields will be correctly written. This write function takes care of that. So the only thing we need to actually change is the update coefs function, which is called for example, when you do solve the equation, you call correct boundary condition. Correct boundary condition evaluates the boundary conditions, and then evaluate usually calls update coefs. So this is the only function that we need to change. All other functions we will simply inherit from the fixed value fv patch scalar field, and we will override only this virtual function. So now I think we have done everything that needs to be done in the header file. Now we should take a look at the implementation or .c file. So here we have already changed the names. And first you have constructors, definition of constructors, definition of member functions, and that's basically it. So now let's take a look. Actually, let me just do it on 2 screens so it's easier to follow. Oh, my connection is a bit slow. Now I'm going to open in the left window header file, because I can see the private data members listed here, because I need to initialize those in my constructor initialization lists. So this is the first constructor, and this is a member initialization list with an empty function body. So we can define everything, initialize everything here. These are all members associated with total temperature. We're just going to remove them, and now we're going to initialize psi max by default with 0, and then we have psi min and psi what's it called, threshold, also with 0. Now we have one of the copy constructors. You can recognize it by average controlDict patch field reference. Actually, this is a mapper. And the first, of course, I forgot to mention the first member, the first thing in initialization list is basically the initialization of the underlying base class. So you just call the constructor of the underlying base class. And here we will just use easy copy syntax. So psi max equals ptf, which is a patch field basically and you gave as an argument, and we will copy the values from there. I just delete those, copy this one. Again, we have psi minimum. Oh, I really need this one here, and then we have psi threshold ptf psi threshold. Now we have a constructor from dictionary. This is basically the one that we're gonna need and use at the moment. It will read the 0 psi file from boundary field entries, and construct the patch field accordingly. So now we need to do something about initializing psi max. So psi max is a scalar, so we need to use the function read scalar, because scalar is basically type def for float or double, depends on how you compile it. But it's basically, what's important is it's a built-in type, so you need to use special function called read scalar to convert input stream obtained from dictionary lookup to a scalar. So let's say we're going to search for the keyword maximum value. That's it. We're going to delete these 5. Oh, wrong button. Sorry. Psi minimum, read scalar, dictionary lookup minimum value, and now we need a threshold value. threshold value and psi threshold. Now this is something what we would like to do. If in the dictionary we specify the value keyword, we will just use the operator equals to assign these values to our patch field using this syntax. Else, this is something related to total temperature boundary condition that we do not really need. Let's take a look at another constructor. So this one is this is the ordinary copy constructor. So psi maximum tppf sf name psi maximum. Let's delete the old ones. Psi minimum, threshold, psi threshold. This is a bit boring work, but I wanted to do it step by step so you can get familiar with it. So this one is also a copy constructor given a different internal field, and we're just going to copy these here. Now, and of course there's an extra comma here which would cause the compiler to complain a bit. So regarding member functions, we have mapping and reverse mapping functions. This T0 was related to total temperature boundary condition, sort of an additional scalar field that we don't need and don't have. So we can just delete these few lines of code. And the update coefs functions, where we will do our thing basically. But first of all, since we have we got rid of these SN grad and gradient internal coefs and gradient boundary coefs from the header file, we're just going to inherit them from the fixed value FV, inherit their definition from fixed value FV patch scalar field. We can just delete these. And before we go into update coefs function, we will redefine the write function. So here you have a lot of total temperature had a lot of default values, so this is why you have all of these ifs. But we just gonna write the keywords, write our own keywords. So the first one was psi max. Actually it was maximum value, because we are searching for, in the constructor we are searching for maximum and minimum value. These are the basically names that are going to be looked up, and these are the names of the private data. So we need to specify the names of that are going to be looked up. So maximum value, we're going to write maximum. We're going to write this keyword followed by value, its value, and then we're going to print a token for the end statement and a new line. We can delete all of these old values associated with total temperature boundary condition, and we can just copy this one 2 times. We have maximum value, we have minimum value, psi min, psi threshold, threshold value. And you can see here that I've went across 80 characters per line, which is a bad style. So I'm just going to break this line like this. So basically what this means is when you call when the dot write is called on a field, it will write the internal field, and this takes care of writing specific boundary fields, basically patches. So if we have a boundary condition called average controlDict per scalar field, it needs to write its maximum value, minimum value, and threshold value. If you forget to redefine this function called write, you will probably have problems with restart, because you will not be able to find, you wouldn't be able to find these values. And here I have a spelling error, maximum value, minimum value, and threshold value. I hope my spelling is fine, but the compiler will tell me if it's wrong. So now let's go to the important part, and this is basically the function that we're gonna need to change, called update coils, which will do our controlling. So the first off is, if this has been already updated, we don't need to do anything, so we're just going to return. But otherwise, we need to do something. These all lines of code are basically related to total temperature boundary condition. But first, let's write our sort of a pseudo code. First, we need to access the dimensioned internal field. This is basically the cell-centered field with dimensions, which we will use to calculate our average, and then we will calculate cell volume weighted average of the field, and then we will set the fixed value boundary with respect to specified threshold value and calculated average value. So let's first figure out how to access the dimensioned internal field. Let's do it step by step. So in foam finite volume library, you have fvpatch field .h. This is the class that we have derived our own class from. And here you have dimensioned internal field, and if you search for, but this is a private data, so we need an access function, and the access function is called dimensioned internal field. So we're going to say constant dimensioned field, type is scalar, and mesh is, it's a volume mesh, so cell-centered field. We're just going to take it as a reference, no need to copy it, and we're going to call it psi in, and we're going to say this dimensioned internal field. So we will just access it through this pointer. Now this gives us the access to the dimensioned internal field. The next thing we need to do is calculate the weighted average of the field. So this one will return a dimension scalar, because this is a dimension scalar field, and we're gonna, all of these are constant because we don't intend to change them in this function body, and it's always a good practice if something is constant to define it as such. It doesn't cost anything, no compilation or runtime overhead, and it's a good style because it increases readability. So dimension scalar, we're going to call it psi average, and now let's take a look. This might be a bit tricky, so I will just briefly go through it. If I go to foam library dimensioned field.h, I expect there's a function called average. Yes, there is. This is arithmetic average, and this is the weighted average, and returns the dimension scalar. So what I need to do, this is a member function, so I need to say psi in dot weighted average, and I need to give it a field to perform averaging with, and this field is basically cell volumes. Now from before, I know that from the infinite volume mesh, I have cell volumes here returned as a dimension field. So I just need a way to grab the first from the patch, get to the mesh, and from the mesh get the cell volumes. And the easiest way to do this is if you go into fields, fvpatch fields. There's a big possibility that someone did this. Go into derived and then just grab mesh. Hopefully this will not cause too much output. It did, but hey. So this is how basically you can get to the mesh using patch. First get fv patch, and then get fv boundary mesh, and then from fv boundary mesh get the mesh. So now we're just gonna say patch, dot boundary mesh dot mesh dot v, and this is how we get the cell volumes basically. So we're going to calculate the weighted average of the internal psi field by giving it volumes which we have access through finite volume patch. This member function of fv patch field returns fv patch, and that one has a reference to fv boundary mesh, and fv boundary mesh has a reference to mesh, and mesh holes are volumes. So this is how we have calculated cell volume weighted average of the field. And now we need to set the fixed value boundary with respect to the calculated value and the threshold value. So we're going to say something like this: if psi average, and don't forget we have to say dot value here because this is actually I'm getting ahead of myself. Let's just do it like this. So we have if psi average is larger than psi threshold. To be honest, I forgot whether this is called psi threshold. Let me just check. So applications, OpenFOAM training, SRC, my boundary conditions, average controlled fv patch field.h. Yes, it's psi threshold, of course, with underscore. So psi threshold is a scalar, and this is a dimension scalar. So there is no operator greater than for dimension scalar and the scalar, so we need to take the value from the dimension scalar. We're only interested in its value, not its dimensions or anything else. So if the average value is greater than the threshold, we were gonna update our fixed value boundary conditions to correspond to the psi minimum. So we're going to say, we're going to call operator equals, which is defined in a fixed value fv patch field, and we're going to say psi max. Psi minimum. If the threshold is exceeded, we're going to use the minimum value. Otherwise, we're going to use the maximum value. And I hope that's it. We just need to get rid of these things related to total temperature boundary conditions, and then we will call update coefs from fixed value fv patch scalar field, because we want to set the flag, the updated flag, to true. So let's go through it one more time. So we first access the dimension internal field and then calculate cell volume weighted average of the field, and then if the average is greater than the threshold, we will use the minimum value. We will force the minimum value, otherwise we will force the maximum value. So hopefully that's it, and if I try to compile, everything will work, although it's really rare that it works from the first time. Let's take a look. So yeah, I forgot to mention, when we compile libraries, we use InFOAM extend, at least in OpenCFD, I think it's automatic. We use wmakelibso because we want to basically say that this is not a binary, this is sort of a source object, shared object library that we are going to compile. And of course I have an error. Now it says here that at line 143 in .c file, yeah, I misspelled boundary. So if I go average control.c, line number 143, weighted average boundary mesh. Now this should do the trick. Hopefully that's the only error. Yeah, it says here that the library my boundary conditions is up to date. If I do wmakelibso again it says it's up to date. Now let me just take a look at wmake files again, and here we specified to put it library in the foam user libbin. Oh, what did I do? Sorry. If I do echo foam user libbin and go inside and do ls-l. I have actually ls-l lib my boundary conditions. Just moments ago we have lib my boundary conditions .so. So now that we have made basically our first boundary conditions, we would like to run some test cases. So if I go to run and OpenFOAM 11 training, from the previous tutorial we have passive scalar cavity. I'm just going to copy that one and call it passive scalar cavity controlled BC. I'm going to remove all of these things. And okay, yeah, I need to also remove inside field. The internal field was overwritten by set fields. Let me just remove it and specify everything to 0, uniform 0. Now what we would like to do is at our moving wall, again this is a cavity test case, so we have a moving wall at the upper boundary, and at the moving wall we will gonna use average controlled boundary condition. And if you remember from the header file, we have 3 private data members, psi max, psi min, and psi threshold that we need to define. And if we go into the constructor for the from the dictionary, we're going to read the scalar by looking up maximum value, minimum value, and threshold value. So if I'm going to say first maximum value is equal to 1, minimum value is equal to 0, and then threshold value is equal to 0.5, let's say, and the initial value, let's say it's going to be 1. So basically what I'm trying to say here is I'm going to use the maximum. So let's say that our psi is sort of an ink, represents an ink in the system, and 1 means the ink, we have 100% of the ink, and 0 means that we have 0% of the ink. So we're going to use this average controlled boundary condition to switch between the maximum value, which is 100% of ink, and the minimum value, which is 0% of the ink, when the average value in the internal field exceeds 50% of the ink. So now let's run the simulation, but before we run the simulation, let's just run it for a bit longer, let's say 50 seconds, and write, for example, each 500 iterations. And let's take a look at the transport properties. This is the diffusion parameter that we're going to use, the old one. And what I would like to see is first the ink. So since there is no flux through the moving boundary, there is no convection transport there. So first we should be hopefully able to see some diffusion transport inside the domain, and then when the diffusion transports happen, then the convection will take its turn and smear everything in the computational domain. Actually, hopefully, we'll see. So now let's run our application, passive scalar icofoam, write it into a log file, and of course foam fatal error, gradient internal coefs cannot be called for a generic FV patch field. Actual type, average controlled. Of course, I forgot to, this is a nasty error because it cannot find this boundary condition, and I forgot to include it in the control dictionary. In the control dictionary, since I didn't compile my top level solver with this library included, I need to dynamically include it here in the control dictionary, which is a nice thing because then that means you don't need to recompile. So I'm just going to say libs my boundary conditions .so. Actually it's lib here, and hopefully now everything will work. Yeah, now it works. The boundary condition is found and it's used. So now the simulation is running, and it's a bit slow because I'm connected to my computer, so that's why you see these occasional lags. But let's take a look at it in ParaFoam. So now we have passive scalar controlled PC, and now the simulation has finished. Let's just check. Yeah, and if I do ParaFoam native reader, yeah, let's take a look at the internal field. I have some kind of an error here. It's not a valid scalar field. I'm not sure what did I do. Yeah, I know what I did. Just a second. Excuse me. So if I go and change 0 psi, I forgot value. This needs to be uniform because this is a value for a field, and these are just scalars, and this is expects a field value. So we need to specify the keyword uniform. So hopefully ParaFoam will not complain. Now let's take a look what happens with our field psi. Initially it's 0 everywhere and 1 on the top, and as we run the simulation, hopefully it will get smeared. Oh, is something wrong with the resizing? Yeah. Okay, so you can see here basically already we have more than 50% of the ink in the system, so the boundary condition just switched off from 1 to 0, and then after some time you get a uniform distribution of 0.5, but the boundary condition is 0 up there. So this with this sort of small demonstration, I will conclude today's tutorial. Thank you very much for watching. I hope this will be helpful, and if you have some questions or anything, you can put them in the comments sections and we'll be happy to respond. Thanks again, and see ya.